good morning and to everybody, and thank you for tuning in to this bulletin on this beautiful Sunday morning, the 17th of November, 2024. You're listening to the club station of the Sandton Amateur Radio Club, ZS6STN. It is operated today from the Shack of Angus, ZS6 Golf Oscar Oscar. This bulletin is broadcast every Sunday at 8:45 local time on the following frequencies. 145.700 megahertz FM on the 2-meter band, 7.115 megahertz low side band in the 40-meter band, which I've got a funny feeling is from the Shack of Noel, ZR6DX. Noel, thank you very much for doing that. And then we have Echolink, ZS6STN-R. All right, in the bulletin today, club birthdays, club news, general ham radio news, and then special topic of interest. All right, let's start with some club birthdays for the past week and coming week. This is from my list. We had James Archibald, ZS6STN, for the 15th, and then we had Dwayne Duta for the 16th. I hope you guys had a good birthday. Then this coming week, we've got Christina Bauer, which is on the 22nd. We also had Jan Schubert, ZS6ARV, for the 22nd. And then we got Richard Gills, ZS6 Lima Lima, on the 23rd. I hope you're going to have a good birthday for that. Okay, let me move on to the SRL Bulletin, the news. In the news today, Saturday 40-meter clubs contest, 100 years of SAQ from Sweden, and club news. We begin the bulletin with the news of a silent key. It is with deep regret we announce the key of Pierre van der Venter, ZS6 Alpha, went silent on Sunday the 10th of November, following a motorcycle accident. We extend our condolences to his brother, ZS2 Bravo Killer, and his wife Liz, family and friends. SRL Saturday 40-meter club contest. The SRL 40-meter club contest on Saturday the 23rd of November is a club activity. The scores of individual operators are added together to get a club score. The club with the highest score after 4 contests will be awarded the SRL 40-meter club championship trophy. All amateur radios are encouraged to achieve the worked all good scores worked on 40 meters. Go to page 33 of the SRL contest book for manual for more information. On 100 years of SAQ from Sweden, on the 1st of December 1924, a very low frequency VLF transmitter with the call sign SAQ at the Bulletin radio station in Sweden was put into commercial operation. Transmissions were sent across the Atlantic Ocean to a receiving station at Riverhead and the flying transmitter stations at Rocky Point, both on Long Island, New York. On the 1st of December 2024, 100 years later, SAQ will be on the air to commemorate this event. The unique Anderson alternate from 1924 with the call sign of SAQ is scheduled for one transmission on VLF 17.2 kilohertz CW will begin at 1000 UTC. Visitors are welcome to the transmission hall at Grimson to experience the SAQ transmission. The transmission event can be seen live on the Grimtone YouTube channel. All right, club news. At the AGM of the Antique Wireless Association of South Africa, held on Saturday the 9th of November, the following committee was elected for 2025. President, Chris Turner, ZS6 Golf Mike. Secretary and is Andy Kearns, ZS6ADY. Technical and net controller is Rad, ZS6RAD. Historian is Louis DeVette, ZS6 Sierra Kilo. Members was Wally Watson, ZS6WLY. KZN liaison was Ron Radford, ZS5 Delta Romeo, and Western Cape liaison was John Watson, ZS1 Whiskey Juliet. Propagation reports. Hannes Kutsia reports that the solar activity is expected to be on low to moderate levels. There are currently 5 sunspot regions with a simple to complex magnetic configurations visible. There is a highly probability of C-class flaring and a low to moderate probability of M-class flares. If you want to do your own frequency prediction, the effective sunspot number for the week is around about 103. The 10 to 20 meter bands, or especially in the late afternoons and early evenings, provide lots of DX fun. Visit the website spaceweather.sanzo.org for further information. Then, just some diaries of events. On the 23rd of November is the SRL Saturday 40-meter club contest and the Cape Town Amateur Radio Centre year-end function. On the 23rd and 24th is the CQWWDXCW contest. 26th of November is the closing date for the newbie logs. 27th is the Sandton Power Hour Tech Talk. Then the 28th of November is the closing dates for the 40-meter club logs. And then the 1st of December is start of Youth Month, Yota Month. Put it so, this year is really coming to a close very quickly. All right, is there anything else that anybody would like to add? ZS6STN is now listening.
ZS6HR?
ZS6HR from ZS6STN. Good morning, Keith. Take a round.
Hi, good morning, Angus. Thank you for your bulletin. Sorry, I've just arrived home from Secunda, from launching our balloon yesterday morning. So I've just parked the car and I'm on the handy-talkie in the garden, so I hope I'm coming through okay. So yeah, just to let everybody know, the Baykar balloon event yesterday, it went off very, very well. Unfortunately, the whisper beacon, we seem to have, it's not transmitting, or we weren't picking it up from about 9:45 in the morning for some reason. Maybe we overinflated that balloon and it popped, or I don't know, maybe the cable wasn't tied to the balloon properly and it fell. We don't know, so we'll have to do another whisper beacon. But thank you very much to Stuart, ZR1 Whiskey Tango, for that whisper beacon. Beacon. The SSTV that we put together worked well. That went through, and a lot of people did decode the images, which is pretty awesome. And we will have a winner. I will have to look at the results and see the winner for the Nicolot voucher that we put on the cards to get the quote and the author of the quote. And the VHF SSTV, that worked for a short while and then it stopped. So that something went wrong there. Someone thinks that the battery pack might have been bumped as this balloon goes up. It's not a smooth flight. It bumps all over the place, and maybe the battery pack popped out because it was just a little battery holder with a couple of batteries in it. And that one stopped transmitting. But the APRS beacons and everything, they worked very, very well. The balloons were all recovered. There were 3 balloons launched. Well, the 2 balloons that we were recovering were recovered, and we launched 3 balloons yesterday morning. There was an electrical fault though on the Baykar balloon apparatus. So unfortunately, the parachute did not deploy when the balloon burst, and everything hit the ground pretty hard. But most things, some people's items are in pieces. Maybe some of the boxes are a little bit fractured. Pins are bent and so on. So we'll see what comes out of the repair work that needs to be done. But we did get some images as well. So those have also been posted on the Baykar group. Then I know there was another event yesterday, and that was the antenna build out at Immerentia Dam. Maybe there's somebody else on frequency who participated in that antenna build. I couldn't be there. And I think that went very well. I saw some of the pictures that had been posted, so thank you very much to Gerard, ZS6GVH, for making all the arrangements and running around to get the kits for everyone to build antennas yesterday morning. And I think that was also a great adventure, and the weather was good. And immediately after that was the newbie contest, so I think everyone participated in the newbie contest as well. Upcoming is as you've heard, is the 40-meter club contest. And we really would like to see if we can get in, make sure we're in the top 3. So we need some club points.
ZS6HR from ZS6STN, operated by ZS6 Golf Oscar. Keith, thank you very much for that report back, and thanks for the feedback from the Bucko launch. Not nice when things do a nice high-level drop. Anyway, let me see if there's anybody else who'd like to add anything there to Club News. ZS6STN is now listening.
ZS6HR?
Go ahead, Keith, from ZS6STN.
Apologies, Angus, I did forget about one thing. On the 7th of December, the Saturday the 7th of December, we are going to have a year-end function, and that will be out at CJ's, what we call CJ's, Carly and Jacques' place, where we had the annual general meeting this year, and that's in Bryanston. We will send out all the particulars to everybody on that, but that will be on Saturday afternoon, the 7th of December. I think the 7th is the Saturday. And so it will be a nice event for the club members to get together and have a little bit of a social and to celebrate the year that's behind us and all that activities that have been achieved over the year. Apologies, I forgot about that, Angus. ZS6STN, ZS6HR.
ZS6HR from ZS6STN. Keith, thank you very much for that as well. Don't worry, just hop in if you do think of anything else. Okay, I'm going to move to a topic of interest. This actually comes from a YouTube video that I saw. Very interesting. So I managed to get the transcript from it, and as I said, it was something I saw, and I was like, no, and then I looked at it again, and actually, I was actually it opened my eyes a bit. But anyway, the video was posted by Bulletin, and the topic is, why was it almost impossible to make blue LEDs? LEDs, don't think their colors come from the plastic covers. And you can see, okay, then they were showing a picture of a LED. You can see that because here is a transparent LED, and also glows the same color. The colors of the LED comes from the electrons themselves. The casing just helps us tell difference LEDs apart. In 1962, General Electric engineer Nick Holliker created the first visible LED. It glowed a faint red. A few years after that, engineers at Sandton created a green LED. But for decades, all that there was these two colors. So LEDs were only used in things like calculators and watches. Only if you could make blue. Then you could mix red, green, and blue to make white. And every other color, unlocking LEDs for every type of lighting in the world. From light bulbs to phones to computers to TVs to billboards. But blue was mostly impossible to make. Throughout the 1960s, every big company in the world, from IBM to GE to Bell Labs, raced to create the blue LED. They knew it would be worth billions. Despite the effort of thousands of research, nothing worked. 10 years after Holliker's original LED turned into 20, then 30, and hope for every using LEDs of light faded away. According to a director at Monzo, these won't ever replace the kitchen light. They were used in appliances, car dashboards, stereo sets, and if not for one engineer who defied the entire industry and made 3 radical breakthroughs to create the world's first blue LED. Shikura Nakamura was a researcher at a small company, a Japanese chemical company called Nicha. They had recently expanded into the production of semiconductors to be used in manufacture of red and green LEDs. By the late 1980s, the semiconductor division was on its last legs. They were competing against 4 more established companies in a crowded market, and they were losing. Tension started to run high. Young employees begged Nakamura to create new products, while senior workers called for his research a waste of time and money. And at Nichi, money was in short supply. Nakamura's lab mainly consisted of machinery he had scrounged and welded together himself. Phosphor leaks in his lab created so many explosions that his co-workers had stopped checking on him. By 1988, Nakamura's supervisors were so disillusioned with his research that they told him to quit. So it was
out of desperation that he brought a radical proposal to the company's founder and president, Nomura Okawawa. This exclusive blue LED, and the likes of Sony, Toshiba, and Panasonic had all failed. What if Nakawa could be the first to create one? After suffering losses after loss on their semiconductors for more than a decade, Okawawa took a gamble. He devoted 500 million yen, which is $3 million, likely around 15% of the company's annual profit, to Nakamura's moonshot project. Everyone knew that LEDs have the potential to replace light bulbs. Light bulbs were the universal symbol for bright ideas, but actually terrible for making light. They worked by running current through a tungsten filament, which gets hot, but mostly of the electromagnetic comes from its infrared heat, and only a negligible fraction of visible light. In contrast, LED stands for a light-emitting diode. It's right in the name. LED's primary creates light, so it is far more efficient, and a diode is just a device of two electrodes, which allows current to flow in one direction. So here is how a LED works. When you have an isolated atom, each electron in the one atom occurs in a discrete energy level. You can think of these energy levels like individual seats from a hockey stadium, and all atoms of the same element. When they are far apart from each other, having identically available energy levels, but then you bring multiple atoms together to form a solid. Atoms come together to form a solid, something interesting happens. The outermost electrons now feel the pole, not only have their own nucleus, but one of the other nuclei as well. As a result, there is an energy level shift. Instead of being identical, they become a series of closely spaced but separate energy levels. An energy band is the highest energy level with electrons in it. It is known as the valence band, and the next highest level is called the conductive band. You can think of these like a balcony level. In conductors, the valence band is only partially filled. This means with a bit of thermal energy, electrons can jump into a nearly unfilled seat. And if electrical field is high, you can jump from one unfilled to a next and conduct current through the material. In insulators, the valence band is full. And the difference in energy between the valence and the conductive bands, the band gap is large, so that the electrical field is applied. No electrons can move. There is no available seats. To move into the valence band, the band gap is too big for any electrons to jump into a conductive band. Which brings us to the semiconductors. Semiconductors are similar to insulators, except the band gap is much smaller, which means the room temperature, a few electrons will have sufficient energy to jump to the conductive band, and now you can easily access nearby empty seats and conduct current. Not only that, the empty seats that are left behind in the valence band can now move. Well, already it's nearby electrons jumping into those empty seats, but you look from afar as it is throughout the empty seats or whole is moving to a positive charge in the opposite direction to the electrons and the conductive band. By itself, pure semiconductors are not that useful. To make way for them for more function, you just add impure atoms into the lattice. This is known as doping. For example, in silicon, you can add a small number of phosphate atoms. Phosphate is similar to silicon, so it is very easy to fit into the lattice. But it brings with it one extra valence electron. This electron exists as a donor level, just beneath the conductive band. So with a bit of thermal energy, all these electrons can jump into the conductive band. And the conductive current, since most of the charge that can move in this type of semiconductor are electrons, which are negative. This sort of semiconductor is called an N-type, which N for negative. I should now point out that semiconductors itself is a neutral. It's just that most of mobile charge carriers are negative. They're electrons, so there is almost another type of semiconductor are most of the charges we carried are positive, and so-called P-type. To make P-type silicon, you need to add a small number of atoms to, say, boron. Boron fits into the lattice, but brings a few variances electrons than silicon. So it creates an empty accelerator level just above the valence board. And with a bit of thermal energy, electrons can jump the outer valence band, leaving behind holes. In these positive holes, which are mostly responsible for carrying current in the P-type semiconductor. Again, the material overall is unchanged. It's just that most of the mobile charge carries a positive holes. Where things are getting interesting is that when you put a piece of P and N type together without ever connecting it into circuits, some electrons will diffuse from N to P and fall into holes of the P type, making the P a little negatively charged and the N a little positively charged. So there is now an electrical field inside a piece of material. Electrons keeping diffusing until the electrons become so large it prevents from crossing over. And now we have established the depletion region, an area of depleted of mobile charges carries. There is no electrons in the conductor band and no holes in the valence board. If you connect a battery a wrong way through the diode, it simply expands the depletion region across until the electrical field opposes of the battery and no current flows. But if you flip the polarity of the battery, then the depleted region shrinks, the electrical field decreases, and the electrons can flow from N to P. With the electron falls from the conductor band into the hole of the valence band, the band gap can be emitted as a photon. The energy changes in the electron is emitting light, and this is how light-emitting diodes work. The size of the band gap determines the color of the light being emitted. In pure silicon, the band gap is 1.1 electron volts. So the photon released isn't visible, it's infrared. These LEDs are actually used in remote controls for your TV, and you can be captured on camera. Moving up the spectrum, you can see the first visible light. The first LEDs were red and then green. And why was blue so hard? A photon of blue light requires more energy and therefore a larger band gap. In the 1980s, after hundreds and millions of dollars had been spent hunting for the right material, every electronics company had come up empty-handed. But researchers had at least figured out the first critical requirements, a high-quality crystal. So what material we used for blue LED? It required a near-perfect crystal structure. Any defects in the crystal lattice disrupted the flow of electrons, so instead of emitting their energy as visible light, it is instead dissipated in heat. So the first step in microcoolers proposed to Okinawa was to disappear to Florida. He knew of an old colleague whose lab was beginning to use new crystal making technology called metal organic crystal chemical vapor deposits, known as OCVD. An OCVD reactor essentially is a giant oven, was and still is the best way to mass produce clean crystals. It works by injecting vapor molecules of your crystal into a hot chamber where it reacts with base materials called a substrate to form layers. It is important that the substrate lattice matches the crystal lattice being built on top of it to create a stable and smooth crystal. This is a precise art. The crystal layers often need to be as thin as a couple of atoms. Nakamura joined the lab for a year to master MOCVD, but his time there was miserable. He wasn't allowed to use the working MOCVD, so he spent 10 of his 12 months assembling a new system, almost from scratch. Even worse, his lab mates shunned him because Nakamura didn't have a doctorate, nor any academic papers to his name. As Nachiwa didn't allow publishing, his lab mates, all PhD researchers, dismissed him as a lowly technician. Experience fueled him. Nakamura wrote, "I feel resented when many people look down on me. I developed more fighting spirit. I would not allow myself to be beaten by such people." He returned to Japan in 1989 with two things in hand. One, an order for a new brand of MOCVD research for Nichia, and two, to reveal a desire to get his PhD. At the time in Japan, you could only earn a PhD without having to go to university, simply by publishing 5 papers. Nakamura had used his knowledge to create a new invention, for his chances to invent a blue LED were low, but now he had a backup plan. Even if he didn't succeed, he could at least get his PhD, but now the question was, with the MOC under his belt, which materials should he research? By this time, scientists had narrowed options down to 2 candidates, zinc selenide and gallium nitride. These were both semiconductors with band gap. Theoretically, in the blue range, zinc selenide was the far more promising option. When grown in a MOCV reactor, it only had a 0.3% latent mismatch with its substrate gallium arsenide. Therefore, zinc selenide crystals had about 1,000 defects per square centimeter within the upper limits of the LED function. Its only issue was that while scientists had to figure out multiple different ways to create N-type zinc selenide, no one knew how to create a P-type. In contrast, gallium nitride had been abandoned by almost everybody for 3 reasons. First, it was much harder to make a high-quality crystal. The best substance or grown gallium nitride was sapphire, but its lattice mismatch was 16%. Related, this results in a higher defect, over 1 billion per square centimeter. The second problem is that zinc selenide scientists had only created N-type gallium nitride while using silicon. P-type was exclusive, and thirdly, it was to be commercially viable. A blue LED would have to have a total light output of at least 1,000 microwatts. These 2 orders of magnitude moved than any prototype had been ever achieved. So between the 2 candidates, almost all researchers had focused on zinc selenide. Nakamura surveyed the crowded field and decided that if he was going to publish 5 papers by himself, he'd better focus on gallium nitride, where the competition was much less fierce. The main chairman claim to fame was one development back in 1972, when RCA engineer Herbert Mustroot made the first tiny germanium nitrate blue LED, but it was dim and inefficient. So RCA slashed the project's budget, calling it a dead. 20 years later, scientists' opinion didn't change. When Nakamura attended the biggest applied physics conference in Japan, there were talks on zinc selenide, had over 500 attendees. The talks on gallium nitride had 5. 2 of the 5 attendees were the world experts in gallium nitride, Dr. Isam Arika and his former grad student, Dr. Ashura Amara. In contrast to Nakamura's academic background. There were researchers at Nakara University, one of Japan's best. A few years earlier, they had made breakthroughs. On the first problem, a high-quality crystal, instead of growing gallium nitrate directly on sapphire, first grew a buffer layer of aluminium nitrate. This has a lattice spacing in between that of the two materials, making it easier to grow a clean gallium nitrate crystal on top of it. The issue was that the aluminium caused problems for the MOCV reaction, making it hard to produce a scale. But Nakara wasn't even close at the stage. Back at Nashi, he couldn't even get gallium nitrate to even grow. Normally, in his new MOC reactor, after 6 months, desperate for results, he decided to take the machine apart and build him a better version himself. His 10-month span put together the reactor in Florida were suddenly invaluable. He began following the same routine every day, arrived at the lab at 6, half an hour welding, cutting, and rewiring the reactor. The rest of the day he spent a day experimenting with the modified reactor to see what he could do. At 7 p.m. he would go home, eat and wash and sleep. Nakamura repeated this routine every day, taking no weekends, no holidays except for New Year's. This is the most important holiday in Japan. After a year and a half of continuous work, he came into the lab on a winter day in the late 1990s. As usual, he tinkered around in the morning, grew gallium nitrate sample, and in the afternoon he tested it. By this time, the electron mobility was 4 times higher than any gallium nitrate ever grown. By this time, the electron molecule was 4 times higher than any gallium nitrate ever grown directly on sapphire. Nagara called it the most exciting day of his life. His trick was to attend a second nozzle to the MOC reactor. The gallium nitrate reacted gases had been rising in the hot chamber, mixing the air to form a powdery waste. But the second nozzle released a downward stream of inert gases, pinning the first flow of the substrate to form a uniform crystal. For years, scientists had avoided adding a second stream to the MOCV because they thought it would only introduce more turbulence, but new Nakara used a special nozzle so it would, even when the streams combine, they would remain laminar. So he called this invention the two-flow reactor. Now he was ready to take on Ashigara and Uma, but instead of copying their aluminium nitrate buffer layer, his two-flow design allowed him to make gallium so smooth and stable itself could be used. As a buffer layer on the sapphire substrate, this in turn yielded an even cleaner crystal of gallium nitrate on top, without the issues of aluminium. Nakara now had the highest quality gallium nitrate crystals he'd ever made. But just as he was getting started, things took a wrong turn. While he had been in Florida, Nakara Uma had stepped back from Nietzsche to become. On this day, Nube had been a risk-taking scientist, designing the company's first prototype. It's why, in 1990, an exclusive executive at Matoshu Electrical, an LED manufacturer and Nakara's biggest customer, visited the company to give a talk on blue LED. It's claimed that zinc soda was the way forward, declaring gallium nitrate had no future. This very same day, Nakara received a note from Ika, stop working on your gallium nitrate immediately. Eric had never supported his research and wanted him to end what he saw a colossal waste. But Nakara crumpled it up the note and threw it away. And he did it again and again when a successor of similar notes, a phone call came from the company's management. Out of spite, he published his work on the two-flow reactor without Nisha's knowledge. It was his first paper. 1 down, 4 to go. With crystal formations settled, he turned to the second obstruction, creating a P-type gallium nitrate. Here, Agaja and Amo had again beaten him to the punch. They had created gallium nitrate simply doping it with magnesium, but at first it didn't perform as a P-type as they expected. However, after exposing the electron beam, it behaved as a P-type, the world's first P-type gallium nitrate after 20 years of trying. The catch was that no one knew why it worked, and the process was a radiation crystal. He suspected the beam of electrons was an overkill. Maybe all the crystals needed was energy. So he tried heating magnesium-doped gallium nitrate to about 400 degrees Celsius in the process known as annealing. The result is a complete P-type sample. This worked even better than the shallow electrons beam, which only made the surface of the samplest P-type. And simply heating things up was a quick, scalable process. His work was also revealed why the P-type had been so difficult to make gallium nitrate with the MOCYB. You supply the nitrate with ammonium. But an ammonium contained hydrogen, where there should be holes in the magnesium-doped gallium nitrate. These hydrogen atoms sneaked in and bonded with the magnesium, plugging in all the holes. Adding to the energy of the system released the hydrogen from the material, filling up the holes again. By now, Nicarose had all the ingredients to make a prototype blue LED. He presented it at a workshop in St. Louis in 1992 and received a standing ovation. He began to make a name for himself, even though he had created the best prototype to date. It was more of a blue-violet color and extremely inefficient, with a little output power of just 42 microwatts, well below the 1,000 microwatt threshold for practical use. At Nashi, the new CEO's patient had run out. Inja sent a written orders to Nakamura to stop tinkering and turned whatever he had into a product. His job was on the line. But in Nakamura's own words, I ignored the order. I had been successful because I don't listen to company orders and I trust my own judgment. At this point, he only had one and third hurdle left, getting the blue LED to its output of 1,000 microwatts. A known trick was to increase the efficiency was to create a well, a thin layer of material of the P&N junction called an active layer that shrinks the band gap just a bit. This encourages more electrons to fall into the N-gap conductor into the holes of the P-type valence band. The best active layer for gallium nitrate was already known to be iridium gallium nitrate, which would not only make the band gap easy to cross, but also narrow just the right amount to bring its blue-violet gap, turning down to a true blue. All right, basically I'm going to leave it there because it's mostly the technical of what happened to Nishira. But just a very interesting video. If you guys want to have a look at it, drop me a line, or I can actually ask them to put it on the website. A very interesting video that. Thank you to everybody out there listening. We trust that you've enjoyed the bulletin today. Feel free to give us comments or any constructive criticism. Thank you for the stations who have assisted with relays and broadcasts, and those who have contributed content from time to time. Join us again next Sunday at 8:45 Central African Time for the regular bulletin of the Sandton Amateur Radio Club. This brings a close to the weekly club bulletin for the Sandton Amateur Radio Club, ZS6STN. ZS6STN was operated today by ZS6 Golf Oscar Oscar. Thank you to all listeners and 7-3. ZS6STN now relinquishes all frequencies for general use.